So this is our sender file, phone A. So now I will try to speak something like I am Devanshu and this is our DSP assignment. So hello, I am Devanshu and this is our DSP assignment.
So you can clearly hear here.
Hello, I'm Devanshu and this is our DSP assignment. Hello, I'm Devanshu and this is our DSP assignment. So this is phone A. Now it contains sender file, and this is phone B which contains receiver file. So let's start opening sender file. So as we open the sender file, the timestamp of sender file started, which you can see here. And now as we open the receiver file, and we are opening late, but still as we can see here, its time is 13 seconds, and the block a time is also synchronized with it, like 17 7 18 18. So synchronization is properly working, and you can share the accelerometer and gyroscope reading.
I will be explaining the working of the sender block. So let's start from the top. Here is the audio capture block which records the live audio input from the smartphone's microphone. This block converts the analog sound into digital samples that can be processed in real time. So next is the selector block and the buffer blocks. They are used to manage the audio frames. The selector ensures we pick the desired audio channel, while the buffer uh, groups the samples into manageable frame sizes for further operations. Then further there is a gain block which adjusts the amplitude of the signal. In simple terms, it controls the loudness of the captured audio before we process it. And then there is the processed audio sent to the MATLAB function block named Scrambler. So we name it's Scrambler, and its explanation will be given further. So this block takes the FFT of the audio and uses a key based permutation to scramble the frequency components. The idea is to add a layer of signal security of data masking before transmission. Then the output of the scrambler is then sent passed to the MATLAB function block 2, which is named overlap add fixed. So which applies windowing and overlap add techniques. This step helps in reconstruction the signal smoothly while minimizing spectral leakage. Once we process, the signal is converted to single precision format for efficient transmission using cast to double block. Yeah, so parallel to this, there is a lower part of the model that deals with the motion sensing. So there is accelerometer and gyroscope blocks, which collects the motion data, acceleration and orientation from the smartphone sensor in the three axis X, Y, and Z. These values, along with the time constant, are combined using the MUX block from the single data stream. The combined data is also converted into single precision format before being sent to the final stage, the UDP send block. So this block acts as a communication gateway, transmitting both audio and motion data wirelessly over network to a receiver system for further processing or visualization. So here is the explanation of the receiver block. So the receiver model begins with the UDP receiver block, which captures the transmitted data packets coming from the transmitted sender device over the local network. This block essentially acts as a network input port, receiving both the scrambled audio data and the sensor reading in the real time. Next, the incoming data is the demultiplex using a mux demux structure, separating the audio data from the accelerometer and gyroscope reading. Uh, the sensor values are displayed on the screen using the data display blocks, allowing us to monitor motion parameters such as orientation and acceleration directly from the receiver side. The audio stream path is handled separately. The 2D selector and buffer blocks together extract and organize the audio frames, ensuring proper synchronization and frame continuity for decoding. Then there is the gain block. It is used to fine tune the simple signal audio before it is passed the MATLAB block function, which is named descrambler. So this function performs the inverse of the scrambling process applied at the sender side using the same key based permutation logic. It records the FFT components back to their correct sequence, effectively recovering the original frequency spectrum. These reconstructed frames are then processed by another MATLAB function, overlapped add fixed. So this performs the inverse overlap add operation to smoothly reconstruct the continuous audio signal from the processed frames. After this, the audio data is converted into the int16 format, preparing it for the playback capability. It then passes through the uh, MATLAB mono to stereo MATLAB function, which converts this single audio channel audio stream into the stereo format for the proper playback experience. Finally, the decoded and reconstructed sound is sent to the audio playback block, then which we can then hear using our the receiver device.
So this is the MATLAB function we used on the sender side. It's called the scrambler. The main purpose of this block is to encrypt the voice signal by scrambling its frequency components using a key-based permutation. So the function takes two inputs, first frame in and thus which is the audio frame. It can neither be mono or stereo. It can be either mono or stereo, each frame containing 1024 samples. Second is perm pause, which is the permutation vector that acts as our encryption key. At the start, the function converts both inputs to double precision to make sure the calculations are accurate. Then we define some parameters, frame n equal to 1024, which is the number of samples per frame, and npos equal to 512, which is half of that, because in frequency domain only half of the FFT bins represent the positive frequencies. Next, the code checks if the audio input is valid. If the frame length isn't 1024, it gives an error. If the input is stereo, the two channels are averaged to make a single mono signal. Since we only scramble one channel, this makes the process simpler and avoids stereo mismatch. Then it checks the permutation vector, the key. It must have 512 values, one for each positive frequency bin. This vector decides how the frequency components will be rearranged. After that, the function creates an hand window, which is used to smooth the edges of each frame and avoids clicking or distortion when processed continuously. This window is stored as a persistent variable so it doesn't get recalculated every time. Now comes the main part, the frequency scrambling. First, the time domain frame is multiplied by the window and converted to the frequency domain using FFT. This gives us the frequency components of the sound. Then we take the first half of the FFT output, the positive frequencies, and we rearrange them according to our key vector perm pause. This means every frequency gets moved to a new position, making the audio completely unintelligible. It sounds like random noise to anyone who doesn't have the correct permutation key. After that, the negative frequency components are reconstructed using conjugate symmetry, which is required to make sure that when we convert back, the signal remains real and not complex. This step ensures signal integrity. Once the scrambling is done, we take the inverse FFT to bring the signal back to the time domain. Now we have the scrambled version of the audio, which is still the same length as before but totally encrypted. Finally, the output is again multiplied by the same hand window, and that becomes our frame out, which is the scrambled frame. This frame is then sent to the next simulation block for transmission over Bluetooth. So to summarize, this scrambler converts speech to frequency domain, shuffles the frequency using a secret key, and converts it back to the time domain. The result is a secure audio signal that can only be decrypted by the receiver using the same key. Now this is our second block, which does overlap. So this function is called overlap add fixed, and it is used to reconstruct continuous audio from individual frames after frequency scrambling. In our system, each audio frame has 1024 samples, and we use a hop size of 512 samples, meaning consecutive frames overlap by 50%. This technique This technique is known as overlap add, and it helps to produce smooth continuous output without audible clicks or breaks. The input to this block is one windowed frame of size 1024 cross 1. That's the scrambled frame we got from the previous block. The output is a smaller segment of 512 samples which represents the next hop portion of the reconstructed signal. At the beginning of the function, we define some fixed constant, frame n equals to 1024 and hop equals to 512, the number of samples to move forward for the next output, and buff length equals to 8192. This is the length of the internal circular buffer that temporarily stores overlapping data. Using fixed values like these helps Simulink understand the signal sizes at compile time. The next part pre-allocates the output y, which is always be 512 cross 1 vector. Then we declare persistent variables, a buffer called buff, a write pointer called write ptr, and an initialization flag. These are used to store data across function calls so that the overlap add processes continue smoothly between frames. When the block runs for the first time, the persistent variables are initialized. Buff is filled with zeros, write PTR is set to 1, and the flag is turned on, so the setup happens only once. Next, the function makes sure that the input frame has the correct shape and size, exactly 1024 samples. If it doesn't, then it throws clear error message, so debugging becomes easier. Then comes the main overlap add logic. Then comes the main overlap add logic. The function writes the new frame into circular buffer starting from the current write PTR. If the frame fits entirely within the buffer, it just adds directly. If it reaches the end of the buffer, it wraps around and splits the data into two parts, one at the end and one at the beginning. So this is buffer circular. After writing, the block reads exactly 512 samples. That's the next stop from the buffer add output. It then clears those samples from the buffer so they aren't added again later. Finally, the write pointer moves ahead by 512 samples. If it goes beyond the end of the buffer, it wraps back to the start. This cycle keeps repeating as each new frame arrives, allowing us to continuously reconstruct the scrambled audio stream. So in simple words, this block combines overlapping scrambled frames into one continuous scrambled signal ready for transmission to the receiver. It ensures smooth playback without artifacts, and it maintains a steady flow of data between frames. In the overall project, this block works hand in hand with the scramble function. The scramble encrypts the frequency components, and this overlap add block stitches the processed frames together into a continuous encrypted audio stream.
Uh, this is the first block in our receiver block. This function is called a descrambler and it is used at the receiver side, that is on phone B, to reconstruct the original audio from the scrambled signal that was sent by phone A. It works as the exact reverse of the scrambler function. The descrambler takes two inputs. One is the frame in, that is a scrambled audio frame of 1024 samples. Also, the INV inverse perm pause, the inverse permutation vector, which is the generated using the same key that was used for scrambling at the sender side. This inverse permutation ensures that only the receiver who knows the correct key can descramble the audio and make it intelligible again. At the start, the code converts the inputs to double precision for consistency and defines a few fixed parameters. The frame size is 102 for samples. The number of bins is 512. Hop size between frames is 512. These values must exactly match with the sender side, otherwise the audio cannot be reconstructed correctly. Next, the function checks whether the input frame is mono or stereo. If the audio is stereo, both channels are averaged into one mono signal. This step simplifies the process and ensures uniform scrambling and descrambling for all types of audio inputs. Then the function validates the size of the inverse permutation vector. It must contain 512 elements, one for each frequency bin, so that each scrambled frequency component can be correctly mapped back to its original position. A hand window of 102 for samples is created using a persistent variable so that it doesn't have to be recalculated every time the block runs. This windowing helps to reduce edge discontinuities and maintain smooth frame transitions. After that, the descrambler moves into the frequency domain. It multiplies the input frame by the hand window and computes the fast Fourier transform to conveniently convert the signal from the time domain to frequency domain. This gives us the scrambled spectrum, which needs to be rearranged back to its original order. Now comes the key step, applying the inverse permutation. Using the vector inverse perm pause, the code rearranges the first 512 positive frequency components so that each one returns to the exact position it occupied before scrambling. This operation effectively reverses the encryption process done at the sender side. After restoring the positive frequencies, this function reconstructs the negative frequencies using conjugate symmetry. It mirrors the positive frequency bins in reverse order and takes their complex conjugates. This step ensures that the resulting signal is real valued after IIFT. Then the IIFT, that is the inverse fast Fourier transform, is applied, which converts the D scrambled signal back into the time domain. Finally, the same hand window is applied again for smoothing and the output frame. Now descrambled is ready to be overlapped and added to form the complete recovered audio stream. In simple words, this block takes in a scrambled frame, rearranges its frequency components using the correct key, and outputs a clean rescrambled frame. If the correct key is not used, the audio remains unintelligible, which makes this method effective for secret audio transmission. In the overall system, this descrambler works together with the overlap add block, which then combines the descrambled frames into one continuous audio signal for playback. This completes the secure transmission chain from phone A to phone B. Now this is the second block in the receiver block called the overlap block, which is similar to that of in the sender's block, and this is the code, and it's quite similar to that.